Okay, so here we have a 3-variable system with 3 equations. So if you have 3 equations, 3 variables, you should have a solution to the system. It's not going to be like an inconsistent system or anything like that. So if we want to solve this with Gaussian elimination, we have a certain goal in place for what it looks like. So Gaussian elimination, you'll have something with X, something with Y, something with Z, and then equals some number as your first row. Then your second row, you'll have something with Y and something with Z equals a number. And then your last row, you have something with Z equals a number. And so we set it up in this stair-step kind of process. And that final step allows you to solve for Z. And then you can plug that in to solve for Y. And then you can plug that in to solve for X. So this is the basic form. Sometimes we can just, will make sure, if I can get the eraser to actually work. Too much was erased. But sometimes we'll make it so that instead of like any number, we'll want specifically just X, just Y, and just Z, so that way you don't have to divide. That's the technical Gaussian elimination, where you don't have a coefficient in front of those first terms. Though, if you do, it's not a huge deal as far as the solving process. So using Gaussian elimination you have to do a lot of thinking ahead to kind of think about what is going to be the most efficient way to put it in this form. So if we look at our system that's on the left side, our first equation is essentially in the form we want. We just don't have that a 1 in front of the X. We have a 6 in front of the X, but that's almost in the form that we want. The second equation has an X and a Z instead of a Y and a Z. The third equation has the Y and the Z. So you're thinking ahead and you're trying to get this in your form. And so if we're using the form for Gaussian elimination, we'd probably want to flip-flop equation 2 and equation 3 so that you have equation 2 with your Y and your Z so that it's in the right form. So usually what I will do is kind of label my equations like this, 1, 2, and 3, so that way when I'm taking notes, I'm referring to them by these numbers and it's a little easier to follow. And what we are doing is just interchanging rows 2 and row 3, or because these are basically in a form. So we're going to interchange 2 and 3. So you're just flip-flopping their position. And then we rewrite what we have. And so you want to make sure you have this curly brace because that is part of system notation. That's what indicates that this is a system. So you do need to have that value, that symbol. And so now as my second row, I have 2y plus 5z equals 25. And then my third row, I have 4x minus 3z equals negative 19. So our goal is let's just get it in the right form where you have 3 variables, 2 variables, and 1 variable, and then worry about our coefficients. So we want to try to get just z in that final step. We want to somehow get rid of the x. And this is where things can get really tricky because sometimes there's not a way to do it easily. So, for example, the only way to get rid of x is I'd have to use the first equation. So, and I'm going to renumber these equations as just 1, 2, and 3. That makes it kind of easier if you just keep renumbering them. So equation 1 and equation 3, I can use those to get rid of x. But when I do that, equation 1 has a y, and then I'll have a y in my equation, my resulting equation. And so then I'll get rid of x, but then I'll have a new equation that has y and z. So then I'll have to use equation 2 and use elimination to get rid of y. So we're basically doing the elimination process, and we have to do it multiple times in order to get it in the correct form. But we know for sure we have to get rid of that 4x in equation 3. And so the only possible way to do that right now is to do elimination with equations 1 and equation 3. So I usually do scratch work on the right side here when I do that. So we want to eliminate x in equation 3. That's our goal here. And so our coefficients are 6 and 4 for the x if we use equations 1 and 3. So we want to look at our least common multiple, which would be 12. So we need to get those coefficients to be 12, one of them with a positive and then one of them with a negative. And it really doesn't matter which one's positive, which one is negative. So let's say that I take equation 1 and I multiply that by a -2. And then let's say for equation 3, we multiply that by a +3. So I'm just putting my coefficient in front and then the equation number so I know what I'm multiplying by. And sometimes that's helpful to also write that in here. So this way I can make sure that I have my correct coefficients, and I need to do it on both sides of the equation so that we keep them equal. And since this is an elimination step with just those equations, I'm not even going to bother writing down that equation 2 yet. So I get -12x plus 2y minus 2z equals -2 for equation 1. And then equation 3, when I multiply it, I get 12x. And you can put in a +0y if that's helpful to you. Minus 9z, and then find my calculator to do -19 times 3. And we get -57. So now we're going to use the elimination process here. So we're going to add these equations together, and you'll see that x cancels out. And we are left with 2y minus 11z equals -59. And this is going to be our new equation for, it's going to be the new equation 3. We're going to be basically putting that in that last slot. So now I'm going to rewrite my system. The first equation is untouched. Second equation is untouched. And now our third equation is different. So our goal is we're trying to get to this Gaussian elimination upside down stair step kind of thing. And we need to we're still trying to get equation 3 to have just z. So again, I'm going to just label these as 1, 2, and 3. So equation 3, we want just z, so we need to eliminate y. And we can do that with equations 2 and 3. All we need to do is make one of them the opposite sign. So again, I'm going to just kind of do this on the right. We're going to eliminate y in equation 3. And let's say all we do is multiply equation 2 by -1 so they have opposite signs. So that would give us a -2y minus 5z equals -25. And then we have 2y minus 11z equals -59. So -2y plus 2y is 0. Negative 5 minus 11 is negative 16z. And then pulling out my calculator again, just to make sure I do that math correctly, we get negative 84 on the right. So we have negative 16z equals negative 84. So now I'm going to rewrite all of my equations. 6x minus y plus z equals 1. 2y plus 5z equals 25. And then negative 16z equals negative 84. Now, the last step to put it in traditional Gaussian elimination form is to make sure all of those leading coefficients are 1. So equation 1, you'd have to divide by 6. Equation 2, you'd have to divide by 2. And equation 3, you need to divide by negative 16. Now, for equations 1 and 2, that's going to give us some fractions. And so to put it in traditional Gaussian form, I will write this out, but we're dividing the first equation by 6 so that we have a 1 in front. The second equation by 2. And then the third equation by a negative 16. And actually negative 84 divided by negative 16 comes out to a fraction. So that actually is, if I get it in the right form, 21 over 4. So we end up, when we're in Gaussian form, with this nasty looking kind of thing. We have these fractions. And then when we start plugging in these values for z, we're going to start having to deal with common denominators and all that kind of thing. So what I recommend when you're solving these by hand is, if it's harder, if it looks gross, if you're getting fractions when you put it in Gaussian form, I would not bother with that, and I would use it in the form that I have above that and start solving from there, because it will just be a little bit easier. So if we do it that way, we will start by solving negative 16z equals negative 84, and we're going to solve that for z. So I've already done that, and that gives us 21 over 4. And you want to make sure that you write it as fractions. The only time we use decimals is if it's like a word problem, then it would make sense to use decimals. But if there's no context to it, you're going to keep it as fractions, especially because if you end up having a round of fraction, then it can throw all of your numbers off. So we have found z. Now, I think it's personally easier, as we still have to plug in a fraction, but it's a little bit easier to plug it in when we don't have to multiply by fractions right away. So we're going to plug z into our second equation, the 2y plus 5z equals 25. So we have 2y plus 5, and then z, we have 21 over 4 equals 25. So when people really don't like to deal with fractions or anything like that, you can multiply both sides by the denominator in order to eliminate that fraction. So first, I'm going to just do the 5 times 21 with my fraction here. So that gives us 105 over 4 equals 25. And so just to avoid working with fractions altogether, we can multiply both sides of the equation by 4 so that you don't have to worry about, potentially making mistakes there. So that would give us 8y plus 105 equals 100. And then it's a lot easier to solve. And it's a lot easier than even dealing with the y equals 5 halves z plus 25 over 2. You would still have to deal with some fractions there. There's more of them there. So we'll solve for y. We'll subtract 105, 100 minus 105. Get 8y equals -5. And then divide both sides by 8. And we get y is equal to -5/8. So now we have found z, we have found y, and so now we want to plug it into our first equation so that we can solve for x. And I'm going to use the 6x minus y plus z equals 1, just because that's a little bit easier to work with than doing all these 1/6 kind of things. So we have 6x minus y, so it's -5/8, plus z. Z was 21 over 4, equals 1. So first off, I'm going to we're subtracting that negative, so that's going to be a +5/8. 21 over 4 equals 1. So again, so we don't really have to worry with fractions. We can multiply by the common denominator here. So the common denominator would be 8. So we could just multiply both sides by 8, and that will eliminate fractions for us. So 8 times 6 is 48. 8 times 5/8 will cancel out the 8. 8 times 21 over 4, you can basically do 8 divided by 4, which is 2, and then multiply that by 21, so that's going to be 42. And then we get 8 on the right side. So we have 48 plus 47 equals 8. Oh, I missed my x, 48x. Subtract 47 from both sides. We got 48x equals -39. And then divide both sides by 48. And we get -39 over 48, which is a pretty nasty looking fraction. And you're not going to want to try to divide that or put it as like a decimal. It's just, we want to leave that in fraction form, so that way when you check your answer, you can, you'll get exactly the right side on everything. So are there any questions so far on this solving? I know that there's a lot of steps, and these solving multivariable systems do take a lot of steps. If I try to zoom out to show every step, this could take like a whole piece of paper. I can't even get the whole thing. I'm trying to zoom out. I can't even get the whole thing out there. It will take like a whole piece of paper.
I have a question.
Yes.
So in the original equations, you swap 2 and 3. Do we actually really need to swap it? Can we still solve it, leaving equation 2 in the original place?
Yeah, if you are doing the Gaussian elimination process, you have to swap them. Okay. But in the real scheme of things for solving, I'm not looking, did you follow this process exactly? I'm looking, can you solve this? So there is nothing wrong with not even doing that step. And honestly, for solving a system like this, I would probably do more of a substitution kind of solving than I would with this Gaussian elimination, because I could maybe solve the third equation for y and plug it into the first equation. Then I have only x and z, and then I can use elimination there. And I feel like that is actually fewer steps. So
with the substitution, we can use a 3-variable format to.
Yes.
Okay.
Yes. Yeah.
Okay.
So, and you can, you know, if you want, you can do that to check your work here. For a 3-variable system like this to check your work, especially when we have nasty fractions like this, what I would do is just use like some sort of calculator where you can check these. Now, Desmos, you can't graph 3-variable systems. It doesn't let you because it's only 2D. So we can't even really solve this with graphing, but you can still kind of plug in your values for X, Y, and Z and verify it. So I'm going to just pull Desmos over here so that you can see that even if the graphing part is useless, the actual other part of it can still be helpful. So what you could do, and so I want to plug in like my X, Y, and Z. So I got Z equals 21/4. Y equals -5/8. And then X equals -39/48. And you definitely want to check your answers when you're solving all these things because it's really easy to make a math mistake. So now to check those answers, I'm going to enter in the actual system that I started with. Because you don't want to do the system after you started moving things around because then you may have made a mistake in those steps. So I just want to make sure. Oh, it's trying to graph. Why is it? I don't know why it's trying to graph it. If I just do, should be, oh, no, X, Y, Z. It really wants to do graph it. And okay, let's see if there's a way I can do this. Yeah, nope, it really just does not want to evaluate it. It usually works when you have X and Y, but I guess with the 3 variables, it doesn't want to do that. So let's go back to the home page. Let's see if I can do this with the scientific calculator. I don't know if it will let me do set X equal and Y equals, that kind of stuff. So let's see, what was Z again? Z was 21/4. I really want to find a way for you guys to check your answers here easily without like making mistakes plugging numbers in. (39/48). So let's see if I can try this again. -6x minus y plus z. Okay, so there we go. So it works if you're in the scientific calculator, the graphing part, it just doesn't like it. So you can see, okay, first equation, using those x, y's, and z's that I solved for, did get 1, which is what we want on the right side. So that verifies. Then let's check the second equation, 4x minus 3z equals -19, or it's z, okay. That equals -19. So that's correct. And then I want to check the last equation, 2y plus 5z, and that gives us 25. So that works. So if you use the scientific calculator, you can put in your x, y, and z, and then put in just the left side and then see if it comes out to the right side. And if it does, that tells you that you solved it correctly. If it doesn't, that's where you need to start looking backwards at your work to see if you made a mistake. So for this particular system, I mentioned that I would have probably solved the second equation for y and plugged that in. So I will just kind of do that over. We'll do this in gray kind of over here. So that second equation that we have is 2y plus 5z equals 25. So if I wanted to try to do some sort of like substitution on it, I might solve this for y. So I subtract 5z from both sides. Come on. Now I am going to still kind of get fractions here, because this is just one of these systems that you're going to get fractions. You can't avoid it. But say I solve this and I got 25 over 2 minus 5 halves z. And then I plugged that into our first equation. So our first equation was 6x, go back to it, minus y. So I can do substitution. That's minus y, and then we had plus z equals 1. So if you're someone that likes substitution, you can do substitution here. We would get 6x minus 25 over 2 plus, because the negative and the negative, 5 halves z plus z equals 1. And then what I would probably do is once again multiply both sides by 2 to get rid of those fractions so that you don't have to worry about that. So 12x minus 25 plus 5z plus 2z equals 2. I can add the 25 to the right side and add those z's together. So we get 12x plus 7z equals 27. And then that gives me an equation that I can use if I go all the way back to the beginning. I can use it with my 2y plus, not 2y, 4x minus 3z equals negative 19. And I can use elimination at that point. Or if you wanted, you can do substitution again. So you don't have to do this Gaussian elimination process. The advantage to it is that it helps keep you organized because you kind of know exactly what you're aiming for, but you don't have to. You can kind of look at the equation that you're given and think ahead and say, well, what might be a different way that I might want to do this? Like maybe instead of solving the last equation for z, I wanted to do it for y, I did it for z. Or maybe that first equation, I might have solved that for z and plugged it into both equations, both equation 2 and equation 3. And then that would have gotten rid of z in both of those, and I would have had just x and y. So there's lots of ways that you can do this. It's more of a what makes sense to you kind of thing, whether you just want to stick with the Gaussian elimination or if you want to try substitution. It's just you do have to kind of keep things, keep track of everything you're doing. And when you do that, I do recommend rewriting your system. So like, let's see, I just changed the first equation to 12x plus 7, plus 7z equals 27. The second equation I didn't touch, so that's 4x minus 3z equals negative 19. And then that third equation I had solved for y. If you want, system notation, we don't have to have everything on the same side when we write it in system notation. So you could just write it like this just to help you keep track of what you're doing. And then you can see that we can do elimination for the first two equations there for x, and then that will give us z. And then we've solved for z, and then you can plug it in for y, and then you can go from there to solve for x. Are there any questions? Okay. I do want to trying to see if there is. Okay, there is a word problem that involves 3 variables that I want to kind of go over so that you guys can see see this in context. So I'm going to just take a screenshot of it. If I can, come on. There we go. Because that way you can see, okay, how do I write my equation? And then how do you then solve from there? So let's see if I can get this. Okay, so I'll zoom in. So this is coming from section 7.3. This is the end of section exercises. So a health insurance company advertises on television, on radio, and in the local newspaper. The marketing department has an advertising budget of $42,000 per month. A television ad costs $1,000, a radio ad costs $200, and a newspaper ad costs $500. The department wants to run 60 ads per month and have as many television ads as radio and newspaper ads combined. How many of each type of ad can the department run each month? So, word problems, when you're doing word problems, read through the whole thing before you start doing anything, and then determine what are you looking for. So it's that final sentence that's telling us what we're looking for. How many of each type of ad? So we have 3 variables: television, radio, newspaper. So let's say those are going to be my variables. So the way that we write this is say, okay, let T equals television. Let's do R for radio, and then N for newspaper. And I did a capital T just so that a lowercase t doesn't look like a plus sign. So I just wanted to make that one capital so that I don't get confused. But it's always good to write down your variables so that way you know what are you looking for, what letters are you using. So once you determine that, then you start reading the problem a second time to determine the information that you have and how you get that into equations. So the first sentence is not important because it doesn't give us any numbers or anything. It's just reinforcing that we have 3 things that we're looking for. Second equation, or second sentence, the marketing department has an advertising budget of $42,000 per month. So what that is telling us is that the total money that we can spend is equal to 42,000. And total always means that you're adding. So we're going to be adding our costs together. So this is going to give us some equation where we're solving, we're adding things together, they're going to equal 42,000. Second sentence, we have a television ad costs $1,000, a radio ad costs $200, and a newspaper ad costs $500. That information is needed so we can take that equation about the total spending and write it as the total. So when you combine that information, this gives us an equation here. So our television is $1,000 per television ad. So you multiply that by the number of television ads. And we are finding the total, which is addition. Then the radio ads cost $200. So we need to multiply that by the number of radio ads we're going to have. And then newspaper is $500. And so we multiply that by the number of newspaper ads. And then the total that we can spend is $42,000. So that gives us our first equation based off of the total cost. Okay, the next sentence, the department wants to run 60 ads per month. So that actually, if we have 60 ads per month, that tells us our total number of ads is 60. So the total for television, radio, and newspaper is 60. Total ads equals 60. So that gives us an equation. Television plus radio plus newspaper equals 60. Now that sentence continues on and it says we have as many television ads as radio and newspaper ads combined. Radio and newspaper combined, so you're adding those together, and that equals the number of television ads. So that our television is equal to radio plus newspaper. So that's our next equation. And we don't have to put that in our system written that way. We could literally put t equals r plus n. But if you do want to put it with all your variables on the same side, you would need to subtract r and subtract n, and then you end up with 0 on the right side. And then this is your system. And so I'm going to put that in the system notation with the curly braces. So when you're solving a problem like this, you need to make sure you're writing down all of your equations and then write down your system before you start doing any solving on it, because we want to make sure you've got all the equations written down correctly. So like when you're working on the application assignment, make sure you've got your system, all of your equations written down before you do any solving, because we want to make sure that you've got them, you've got all the equations correct. So I'm looking at this. I'm wondering if there's a department wants to run 60 ads per month, have as many television ads as radio and newspaper combined. So I'm looking at our system right now. And if I added equation 2 and equation 3, I would get t equals 60, which means there would be no radio and no newspaper ads, and that doesn't make sense. So I'm thinking, I'm looking to see if there's any error in my equation. Does anybody see anything that looks off with our equations here? There might be, I'm looking, I don't see anything, but it just doesn't make sense that you would solve this and then you would end up with no radio ads and no newspaper ads. Oh, I'm mentally, okay. I figured it out, guys. I was trying to mentally add the equations in my head and I added wrong. So we're correct here. All of our systems are correct. So as I was saying, what threw me off is I was looking at, let's add the equations 2 and 3 together here. And when I added, I forgot that if you add those together, t plus t is 2t. So it's not t equals 60. It's going to be 2t equals 60. So that's my mistake. So I'm going to write this out. This is why it's not always good to do things mentally in your head. So we can add these two equations together. Oops. And we get 2t, r and n eliminate, and then that gives us 60. And then when you divide both sides by 2, you get t equals 30, which makes much more sense. So notice that I'm not using Gaussian elimination here. I'm not trying to put it in that form that I had all the way up here, because it just doesn't make sense when I can find one of the variables immediately without going through this whole process. So you don't always have to do a Gaussian elimination. You can take what you look at and say, oh, I can eliminate r and n if I use those two equations, and then that gives me t. So we know that t is equal to 30. So I'm going to just kind of rewrite our equations just so you can visualize what we've got here, because then we have to figure out, okay, R and N, we need to solve for those. So that gives us, I'll put it over here, 1,000 T. So when you plug in 30 and then you multiply by 1,000, we get 30,000 plus 200 R plus 500 N equals 42,000. And then we have 30 plus R plus N equals 60. And then 30 minus R minus N equals 0. So that's sort of where we're at right now. And I'm just immediately plugging that in for T so I can kind of look at what we have. So now we want to solve for R and N. And it's sort of up to you on what you want to do, whether you want to continue elimination or if you want to do a substitution. Personally, if I look at this, I might then go from substitution. So I might take equation 2 right here and solve for R and then plug it into equation 1. And we don't want to plug it into equation 3 because we already used equations 2 and 3 together. So this is a good example of where Gaussian elimination is not necessarily would not necessarily be the best way to go about this. So I'm going to take equation 2, and first I'm going to solve it for R. So that means I'm going to subtract 30 from both sides and subtract N. So we R equals 30 minus N. And then I'm going to replace that in equation 1, where we have 30,000 plus 200 times R, which is 30 minus N, plus 500 N equals 42,000. And I'm going to use substitution here just because I think it's easier. So I plug in, distribute, and now we're going to solve for N. Actually, first thing I'm going to do is just move this 30,000 to the other side because I can do that pretty easily. And then I'm also going to distribute the 200 through here. So that gives me 6,000 minus 200N plus 500N equals 12,000. We can subtract our 6,000 from both sides and combine the negative 200 plus 500. So that's 300N equals 6,000. And then I can divide by 300 and that gives us 20. So now we know that there are 20 newspaper ads. And then from here, we can just plug it back into the equation that I've solved for R, and we get R is equal to 10, because 30 minus 20 gives you 10. So we've solved this. Now, because this is a word problem, you don't want to just do the math here and then leave it at that, because you want to make sure it's very clear what you're communicating and that you're communicating the answer to the question. So the question asks, how many of each type of ad can the department run each month? So you should be answering this in a sentence to make it very clear. So the department can run, and see, we got 30 for the television ads. 20 newspaper ads, and 10 radio ads. So you want to put this in a sentence because then it's very clear in context and you're actually answering the question that's asked. So the question, how many of each type? Now I've answered it. 30 television ads, 20 newspaper ads, and 10 radio ads. If you just gave your variables, I used variables that make sense, T, N, and R, but if you use X, Y, and Z, X, Y, and Z doesn't make sense. It'd be like, well, is X radio, television, or newspaper? Which one of those does it? It's not clear which variable that goes with. So it's best to put it in a sentence so that you're making it very clear what your answer is, and you're making sure that you're answering the question. And you should always then reread the question to make sure that your answers make sense. And the key here that I would definitely make sure if it makes sense is as many television ads as radio and newspaper ads combined, because those are frequently translating something like that to an equation is usually, I've seen a lot of people do them incorrectly. So I'd always double check at the end to make sure that what you have matches that. So radio and newspaper ads, that was 20 and 10, so that gives us 30. That's the same number as television ads, so that works out there. And then 30 plus 20 plus 10 gives us 60. And then you can just check it in your last equation and make sure that everything comes out to 42,000 per month. And if all of those check out, then you're good and you've solved. But you want to make sure, like when you're taking notes here, you label what your variables are. You want to make sure that you've got your system very clearly written down with the system notation, the curly brace, so we have your equations. And then from there, as long as your work is easy to follow, like if you just want to do arrows like I was doing, that's fine. I can kind of follow arrows from there, whatever you want to kind of do. I can usually, arrows I can follow pretty easily. It's mostly making sure that the equations are written down so that way I know what equations you're even solving. Because I've seen people skip that step and then it's like, well, wait a minute, where did you even start? So, and then making sure that you've got your final answer there. And it's really good, show every step, because then if you do make a math error, I can find where it is. If you start skipping steps, then I don't know where your error may occur. I may know that your number is wrong, but I won't know how you got that number, what you did to get that, where you went wrong. Are there any questions?
I have a question on the from the textbook and the example 5, if I can go there.
Sure, I've got the textbook open. Let me pull that up.
It's the system with infinitely many solutions. Example 5.
There we go.
7.3.
Mm-hmm.
So the textbook is getting down to solving for x, and so it's determined that y is equal to z. Plug that back into equation 1 and spits out a x of 2z minus 1, and I'm not exactly sure how that was determined. So if you can just kind of write that portion of it and show me how that was solved, that would be all I would need for that. Thank you.
Sure. Okay. So I will just, oh wait, that's not what I'm trying. There's a fancy, there we go. I'll do the snip and sketch. So we will just, there, I'll just take a screenshot of this.
Sounds
okay.
Good.
So we got y is equal to z.
Yep.
So if I take this equation for x plus z instead of y, minus 3z equals -1. So we add the z's together. That's 1z minus 3z. So 1 minus 3 is minus 2. So that's minus 2z equals -1. Oops, I forgot my equals. And then you add 2z to both sides.
Okay, wait a sec. So you're adding the y's and the z's to give you 2 I guess
So
I'm not.
we replace y with z because y is equal to z. So instead of having y, instead of x plus y, it's now x plus z.
Oh, okay. I was keeping the y in there.
Yeah, so we're replacing it with z, so that way we have something with just z. It's a substitution, essentially.
Okay.
And
Okay.
then that's how we get the negative 1z, negative 1 plus 2z, or you can write it as 2z minus 1.
Okay. Okay. Thank you.
You're welcome. Are there any other questions on these kind of systems that I can answer? Okay. For the one question on the assignment about the fertilizer, I have a video in, let me pull that over. So if you go to videos here, and it's also, I have a link also in the week 2. So it's this modeling using systems of equations. The very last example here, when you have different parts of something, I go through an example that's similar to the fertilizer. It's not going to be exactly the same, but it's going to be set up the same way. So if you're really struggling on that one, watch this video to help you set those equations up, because that's probably the hardest question on the whole assignment. And it's hard because of the setup, not necessarily with the solving, because once you get it set up, you can eliminate fractions and then you can solve for there, but it's a setup that's tricky. So I'd make sure you watch this video. And that's